Swayam Prabha. Digital India. Educated India.
P&T NBP
Yeah. First you finish off the entire prefix sum completely. Then you will get another, you will get all these fellows. Let us say I overwrite it. You want to save, I can even overwrite it, or I can put it in a new location also. So I overwrite it. Then at the end, if you want, which one you want? 150. Then go to the second fellow and take 150 here. Meaning it will be already available. See, this is on full array of n. This will be 1, 2 till n. This is one array of n elements. P1 will read from 1 to n by p. P2 will read from n by p plus 1 to 2n by p. Right? So Pi will read from I minus 1 into n by p to I into n by p. Okay. I minus 1 into n by p plus 1 to I into n by p. Right? So ultimately in the array itself everything will be stored, and you go and read from that array. So there is no. Let me say, no, we will have 2 processors and 8 numbers. Okay. A1, A2, A3, A4, A5, A6, A7, A8. Okay. And this is array B with the index 1, 2, 3, 4, 5, 6, 7, 8. Okay. P1, let us say 4 processors, right? Pi read from I into n by p plus 1 to I minus 1 into n by p plus 1 to I into n by p. This is the first step, read. This is step number 1. So what will P1 read? P1 will read 1 to, what is n by p? N is 8, p is 2, p is 4, n by p is 2. Okay. P1 will read from 1 to 2. P2 will read from 3 to 4. P3 will read from 5 to 6. P4 will read from 7 to 8. Okay. So then what will P1 do? P1 will compute A1 and A1 plus A2. P2 will compute A3 and A3 plus A4 and store in which location? This is store in. So what will happen? Let us see this. Sorry. So P1 will do this, okay. So P2 will do A3 and A3 plus A4 will be done by P2. A5 and A5 plus A6 will be done by P3. A7 and A7 plus A8 will be done by P4. Okay. This it will all do in the same array. This is the B array again. Okay. Right. And this will take 2 steps, n by p steps. After that, what will P1 do? So then I will have now P1, P2, P3 and P4 will take A1 plus A2, A3 plus A4, A5 plus A6, A7 plus A8. And now it will do what? It will do a prefix sum. So then what will happen now at the end of this? A1, A1 plus A2, A3, A1 plus A2 plus A3 plus A4, okay, A5, A1 plus A2 plus A3 plus A4 plus A5 plus A6, A7, A1 plus A2 plus A3 plus A4 plus A5 plus A6, plus A7 plus 8. This is what will be there in B. Okay, because it does the prefix of 1, 2, 3 and 4, whatever I have put it as dot here, okay, as you see here. Those things would be saved here, okay, in this location. This is the prefix sum. Now what will happen? Now P1 will take A1 plus A2 and add it to A3. While that is doing, P2 will take this number and add it to A4, okay, and then P3 will take. So now let me just say P1 will take this and add it to this. This will take this and add it to this. Take this and add it. Now I will have all the things. So in B I will have A1, A1 plus A2, sigma till A3, sigma till A4, sigma till A5, sigma till A6, sigma till A7, and of course A8. Okay. Are you getting this? At this point you can query any element and take. So now I want what is B4, no, B7 I want, I can take from that. Okay. Are you able to follow? Right. This is the, okay. The doubt is answered? Okay. Correct. Okay, boss. So what did we learn now from this lemma? Now what is the time complexity? I had n by p time, sorry. So I took n by p plus log p, right, it is n by p time and p processors is n. N by p plus p processor, n by p into p is n, right. So the PT product, the processor time product is equal to the complexity of the best known sequential algorithm. That means this particular algorithm is optimal. Okay. What is optimality in the context of parallel programming? The processor into time product should be equal to the complexity of the best known sequential algorithm. Is it okay? All of you? It's fine? Okay. Now when n processors, okay, let me just I am given n processors and n bits which I want to AND these n bits. What is the time complexity? What is the best time complexity? Log n. But can I do faster? AND of these bits. So let me say B1, B2 to Bn, and I have one bit called S. So initially I will make S as 1, right? Initially S as 1. So each Pi will see if Bi is equal to 0, S is equal to 0. Only one step. Right? If Bi is 0, then S equal to 0. So that means if all the bits are 1, the answer will remain at 1. If at least one of the bit is 0, the answer will become 0. So what sort of PRAM model this algorithm will require? What sort of PRAM model this algorithm will require? Palagat? Exclusive, right? Exclusive, right? Concurrent, right? Everybody is trying to write into S. But note, all the processors, if they want to write, they will write the same value. So it doesn't matter who writes first. For example, let's B3 and B6, B0, right? Irrespective of whoever writes first, B3 writes first or B6 writes first, the answer will be the same. So that's what we told, right? In concurrent, so this is one step. At the end of this step, please note that there could be several fellows who would be willing to write to S, but all of them will write the same value, so it does not matter whichever way we execute it. So, how much time will it take for me to find the n bits? Order 1 time. But in which model? CRCW model. Suppose I am given P processors, how will I do this? I will split it into n by P. So I will get I'll get the A1, A2 to A n by P in AP in n by P time. So I will find the each processor will find the AND of those n by P bits, and let me call it A1, A2 to AP. Now I have P processors and P bits. Now this will take order 1 time. So in n by P time into P, so this is order n. So this is optimal algorithm. So I can design an optimal algorithm which will take n by P time to find the AND of P bits. Are you able to do this? So how will I find R? Same way. What I should do? S is 0. If Bi is equal to 1, S equal to 1. So that way I can find the bitwise R, and again I can do it in parallel time. Okay. Now let us do the last part, next 5 to 10 minutes, which is indeed a bit more complex. So I can do the R of n bits in constant time, I can do the AND of n bits in constant time, and all the processors that write into that common location, in this case it was C, they write the same value. So this is much suited for, it is very clearly suited for the CRCW PRAM model. Okay. So optimality of parallel algorithm is optimal if and only if time taken by the parallel algorithm into number of processors used is equal to time taken by best known sequential algorithm. Okay. So this is how we make it optimal. That lemma, this is the procedure that I followed in both the cases of splitting it to n by P, and then so use P processors and split data set into n by P blocks, P blocks, right, this is wrong. P blocks, allot 1 processor per block, let us take P blocks each of size n by P, okay, and then allot 1 processor per block, and let us take 3 processors and 6 numbers, we did this. Okay. Right. So we already saw. So this was actually invented or proposed by Brent. So this is sometimes called the Brent's technique. Okay, sorry. It's called the Brent's technique, or it's also called Brent's lemma. Both mean same. Okay. Now let us do a much more fascinating algorithm of trying to find the minimum of n numbers. What is the time complexity to find the minimum of n numbers? N. Sequential time complexity is order n. Now let us see. Suppose I want to find the minimum of A1 to An using n squared processors. Suppose I am giving you n squared processor. I can do it in constant time, right? This is algorithm. Let me have n locations called Ci equal to 1, and I have n locations, that will be using n processors, constant time I can finish. Now for all I comma j, if A is greater than Aj, then Ci is equal to 0. Okay, right? That is all. That will use n squared processors. Now note that except for the minimum element, every element would be set to 0, except for all the minimum elements. I can have more than one minimum element also, right? Because if A is greater than Aj, I consider all the pairs I comma j except I not equal to j, of course. If A is greater than Aj, then I make Ci is equal to 0. That means there exists a number lesser than that. So at the end of this, if Ci actually becomes 0, at the end of this second step, that is for a, if Ci actually becomes 0, that means there exists a number which is lesser than that, correct. So at the end of second step, if Ci is still 1, that means there is no number lesser than that, okay, and hence that is the least number. Now what you do, if Ci equal to 1, then B equal to A, again it uses n processes, right. And if more than one fellow are the same, then their corresponding Ci will be 1. So each of these processors will write into B. B is a common location as you see here. So B is a common location. Many processors may try to read, but all of them will carry the same value. If they do not carry the same value, then they would have been set to, right. So at the end of this step, please note that at the end of this step, Ci will still remain, at the end of this for all ij step, Ci will still remain 1 only if it is the minimum. If it is one among the minimum, there could be many elements with the same minimum value. And then I go and say if Ci equal to 1, then I say B equal to A. So several fellows will start writing into B, but all of them will write the same value. If two of them A and Aj, if Ci and Cj actually writes 1, Ci equal to 1, A and Aj are different. Suppose let us assume A and Aj are different, then what would have happened? Either A would be greater than Aj or Aj would be greater than A. Then correspondingly either Ci or Cj would have become 0. Now I say both are 1. So that is a contradiction here, and hence, so using n squared processors, in I can find the minimum of n numbers in constant time. So n squared processors, n numbers, this is about minimum problem. N squared processors, n numbers, constant time on CRCW, right. Okay. Now how will I do it? So let Tn be time required to find the minimum of n processors, minimum of n numbers using n processors on a CRCW PRAM. Okay. Now what I do, if I have given n numbers, I will split up into chunks of root n each. Can I split it into chunks of, so let me call it as B1, B2 to B root n. And for each one of them I will assign root n processors. I am given n processors, right. So for each one of them I will assign root n processors and solve them recursively. So Tn is equal to T root n. T root n is time required to find the minimum of root n numbers using root n processors on a CRCW. So I am assigning root n processor to each of this and solve it recursively. So Tn will be T root n. At the end of it, what will happen? I will have one number for each. Let me call min1 m2 to m root n. So I have n numbers, I have root n numbers. Now I will have n processors because the processors are now relieved, they have. So I have root n numbers and n processors. How much time will it take for me to find the minimum? 1, because n numbers, n and n squared processor is 1, root n numbers and n processors. So this is Tn is equal to T root n plus 1. You are getting this? Okay. So this means let, without lots of generality, let n be equal to 2 power k. So T 2 power k is equal to T 2 power k by 2 plus 1. Let me say that Rk, let us say, so this is nothing but T 2 power k is equal to T 2 power k by 4 plus 2. This is equal to T k by 8 plus 3. Is it T 2 k by 2 power r plus r. And it will stop when k is equal to 2 power r, right, T2, or r equal to log k. When r equal to log k, this will be T1 plus log k. And what is k? K is log n. So this will give you a log n algorithm. K is log n, right? N equal to 2 power k means k is log n. So this will give you a log n. So the idea is that if I have root n processors, if I have n processors and n numbers, I will split it into chunk of root n each and give root n processor to each one of them. So that will take, after that I will finish off in log n. After that I will get root n numbers and I will have now n processors. Root n numbers and n processor I will take constant time. So that is how you get this 1 here marking. So, and since every processor is executing concurrently, I do not need to multiply this with any factor, because all root n subproblems are solved concurrently, each by that set of processors. What is T root n? Time required to find the minimum of root n numbers using root n processors on a CRCW. Now I am giving that process, so it starts working. Okay. And then this is how I derive, show that T of n is actually log n. So n squared processor, n number order 1 time, n processor, n number order log n on the CRC. N processors, n numbers. Now what will happen if I say n by p processors, p processors and n numbers, I will take the minimum of n by p each, then I will have n by p elements. So I will have p elements and p processors. If I have p elements and p processor, it will take log p, right. So n by p plus log p. Since p is very much less than n, log p is still very much less than n. So this is equal to n by p into p processor, I will get order n. So I can use the same Brent's technique to show that I can get an optimal algorithm. So two interesting things. Number one is that if n squared processor, constant time I can find the minimum of n numbers. That is the first simple but very interesting result. After that, how will we use it to actually find this recurrence relation, and how can I get an order log, how can I use it to get an order log n algorithm, and then finally how to optimize it. Okay. So with this we sort of understand what is a CRCW PRAM and a EREW PRAM. CREW is very close to EREW. So I am not taking any specific example there. Now you can start writing. So if you are writing some major parallel program, you should first understand, classify this and start thinking in that direction. Else you may not get that real speed up that you are looking for. Okay. Fine. Any doubts? Are you able to understand this? Any doubts? So if there are no doubts, okay, thanks.